Hello, my name is Michael Huh. I am a geochemistry PhD student at UC Davis, and I am interested in understanding how Earth's atmosphere evolved since the formation of the planet. You have probably heard about the James Webb Space Telescope. It is the biggest telescope ever launched into orbit. One of the main mission goals of the telescope is to measure the chemical properties of planetary systems, such as the atmospheres of planets orbiting stars outside of our solar system. And which planet will these atmospheres be compared against? Earth. By better understanding how Earth's atmosphere evolved, and also where Earth received its volatiles, such as water, we will have a better understanding of when and how our Earth became habitable, and also maybe provide insight into how other planets evolved. The clues as to the provenance and timing of the delivery of the essential elements for life, such as hydrogen, carbon, and nitrogen, are present in the Earth's mantle. However, due to the chemically reactive nature of these elements, the clues have been extremely difficult to decipher. Instead, we use the noble gases as they are chemically inert and thus are excellent diagnostic tools. To access the noble gases in the mantle, we use dredging techniques to collect volcanic gases from the bottom of the ocean along mid-ocean ridges. We select the best samples, free of alteration, place them under vacuum, then release the gases trapped in the tiny vesicles by incrementally crushing the sample. The released gases are then measured with a mass spectrometer, which determines the isotopic composition of the noble gases. What you see here is an example of the data that is produced. Each of the solar system volatile reservoirs have uniquely identifying isotopic ratios. If the terrestrial volatiles were sourced from one of these reservoirs, we might expect the mantle data to look exactly like the reservoirs. However, the mantle data plots closer to the air value. This is because plate tectonics have slowly introduced air-like gases into the mantle, which slowly changed the mantle isotopic values. To determine the source of terrestrial volatiles, we can extrapolate a trend line from air through the mantle value, and we can see here that a major source of terrestrial volatiles are from meteorites rather than the solar nebula. Now, this information can be used to constrain atmosphere evolution models. I want to thank ARCS for their support, as their funding allows me to utilize the latest generation of mass spectrometers and procedures to make measurements that have historically been difficult and often impossible to make. Thank you.